Last day of chapter 6, we're going to combine a little more time with exponential growth and decay, that y equals ce to the kt equation, along with some differential equation work. Neither day is exceptionally necessary, but it probably won't hurt us to practice a little bit more anyway. So we're supposed to find here the exponential growth model for Crystal Lake. So all we really need is we need to know what C is, we need to know what K is so we can fill them in. So my population in 1990 was 18,000. I'm going to call 1990 T equals 0. Population in 2000, we're going to call that T equals 10. So at time 0, we're at 18,000. It's nice to have that because we could call that 18,000. We know that 18,000 is our initial amount. So all we really need is to come up with what K is. And we've got this growth model, and we're ready to go. So how are we going to do that? Well, we're probably going to use this point. At time 10, we had 33,000 in order to solve. So let's take that. Let's take 33,000. Let's put that in for our final amount. Let's put 18,000 in for our initial amount. And e to the k times 10 years it takes to grow from 18,000 to 33,000. So now we start solving. Well, if I divide both sides by 18,000, I'm going to have 33 over 18. And I could make a decimal out of that, but I'm going to have my calculator take care of this for me in a minute anyway. E to the 10k. So now natural log both sides. So my k that I'm solving for is natural log of 33 over 18, all divided by a 10. So that is my constant. So now take your constant, and we're going to pull that, use our calculator to store this again. So let's see. So natural log of 33 over 18. Natural log, whoops, I better get out of there. So natural log of 33 divided by 18. And then we have to divide that by 10, and there's our constant. And we could again go and store that thing, becoming my new favorite command, as our k. Hit enter. There's my new constant. So now when I go back and I look at my equation, I don't have to memorize that number. I've got it. I know that this growth model has my k that I stored there, and now all I would need to know is what t do we care about in order to take that thing and plug it in. So that's a pretty good start. Now this second problem, I don't feel like we need to spend a great amount of time on it. This is another exponential growth and decay problem. We got 10 present at a certain time. We got 35 present 5 hours later. How many will there be 12 hours after the initial time? I'm not worried about A, nor am I worried about B. What I would like to point out on this particular problem, the number of certain type of calendar increases continuously at a rate proportional to the number present. I care about that phrase because when you see that phrase, they're telling you y equals ce to the kt. That is another way to say that this is an exponential growth equation problem. And I'm not going to take the time to go through and do it. You're welcome to go through and do that if you wanted some practice on your own. But the idea here is once you recognize that, now we're going to use 10 for our initial time. We're going to use 35 at time 5, and we're going to find what k is, store c, store k, and then plug your 12 and find your value. In part B, I'm not worried about either, but what scares me on problem like number 2 is that language increases continuously at a rate proportional to the number present. Get used to that, internalize that. We will see that again. Now, some differential equations. So a little bit of practice here separating variables. When you're separating variables, let's make sure that we check and see how many terms we have. We have one term on the left side. We have one term on the right side. So remember, to separate things, you move things around by multiplying and dividing. So I'm going to start by dividing both sides by y. So that's going to leave me a 1 over y with a dy. And if I multiply both sides by dx, that's going to leave me an x over 1 plus x squared and a dx. So there I've rewritten my equation. Now we can integrate both sides with respect to their variable. So left side's going to be natural log absolute value of y. And the right side, we're going to probably do a little u substitution. So the right side, u would be 1 plus x squared, du would be 2x dx. So the x dx that's in the problem would be 1/2 of du. So I'll throw that in, and I'll end up integrating then 1 over u du with a blue 1/2 out in front of it. So if I do that, and I go through and I do my integral, I think I've got 1/2 natural log absolute value of 1 plus x squared plus my constant. So I've taken care of both sides of my differential equation. Now in order to isolate what y would be, we're going to probably do that little e trick thing. So let's e both sides. So if I do that, whoops, let's use a color other than red. So we're going to e it now, to use that technical math term that's really not a math term. So if I do that, left side becomes y, right side becomes e raised to the 1/2 natural log absolute value 1 plus x squared plus my c. Well, we've got a little trick that we could throw in there, because we know that the e and the c are going to turn into that black constant that we've dealt with before. Now this 1/2 could move up and be an exponent for the natural log on the 1 plus x squared. So what I really have here is I have e to the natural log of 1 plus x squared raised to the 1/2 power, and that's my y. But now if I want to clean this up, I'm probably not going to leave e and natural log in the same equation. I'm going to drop those two things out. So if I do that, I've got my c times the square root of 1 plus my x squared for the solution to my differential equation. Or 1 plus x squared to the 1/2 power would be just fine also. So there's a little practice there. And then this last one is just a nasty equation, and what I'm worried about is us being able to separate the variables. So separating my variables, and then we're going to have to ultimately find out whatever c is with that information. So what do we got going here? So this time, instead of having one term like I had up here in number 3 and moving by a multiplication and division, now I see multiple terms. I see 2 terms on the left, and I see a 0 term on the right. So before I can do anything else, my advice for problems like these is always for you not to use y prime, but always rewrite it so that instead of having y prime, you call this dy over dx. It just seems to be something that's more effective for getting variables separate. So if you treat it that way, now you can see, well, I've got y's, I've got x's, I've got 2 terms. I'm going to start by moving this term over to the other side by subtracting it. So I have e to the negative x squared times quantity y minus 1 dy over dx is equal to negative xy. Now I'm down to a single term on both sides, so now it's about multiplying and dividing to get your variables alone. So I'm going to start by dividing by e to the negative x squared to move it over, and dividing by y to move it over. So if I do that, I have y minus 1 over a y with a dy over a dx on this side. And on this side, I have negative x over e to the negative x squared. So I don't quite have my variables separate yet. So now left side, let's see. I should now multiply both sides by dx. So here's what I'm now integrating. Y minus 1 over y with respect to y. And on the left side, if I've got e to the negative x squared power, that would be the same thing as having an e to the positive x squared power on the top, dx. Now we've got something we can integrate. Left side looks like I should split it, so let's do a little scratch work here. So a little scratch work. I'm going to call this 1 minus 1 over y that I'm integrating. So if I'm integrating 1 minus 1 over y dy, antiderivative of 1 is going to be y. Antiderivative of 1 over y is going to be minus natural log of absolute value of y. And on the right side, I think I've got a u substitution going on. So du would be 2x dx, so I'm going to have to throw in a 1/2 and end up integrating e to the u with a negative sign on it. So if I integrate that, I'll have e to the u with a negative 1/2 on it. So this right side will be negative 1/2 of e to the x squared. And then I'll throw my c on. Now, I'm not even going to try to talk somebody into solving for y in that equation because you got lugs and you got y's, and it's just going to be a disaster, so we're not going to do that. So let's go back up here. And we've got the condition y of 0 equals 1. Now remember, the thing that might be a little bit misleading for people here, y of 0 equals 1. When x equals 0, y is equal to 1. So now if we go to solve that, y is equal to 1. So 1 minus natural log of 1 is equal to negative 1/2 e to the 0 power plus c. So 1 minus 0 is equal to negative 1/2 plus c. Looks like my c is going to be 3/2. So my solution to this differential equation would be y minus natural log absolute value of y is equal to negative 1/2 e to the x squared plus that 3/2. And that is a great way to finish off chapter 6.